Hello guys, welcome to Ramta Solutions. Today we will be looking at forces between masses. Okay, we will be looking at forces between masses. So this is where we will be using the Newton's law of universal gravitation. Okay, this is where we will be using the Newton's law of universal gravitation. The law that I just mentioned, you you had the word gravitation. So this means we're going to look at gravity. This means we're going to look at gravity. Now, what do you know about gravity? Is that it is an attractive force. What else do you know about it? It is a non-contact force. All right? It is a non-contact force. So, what we know um, about the power of gravity or the gravitational force is that it is the force that is responsible to keep the moon in its orbit around the earth, right? It is this gravitational force that's responsible for keeping the moon in its orbit around the earth, right? So another thing that we also know about the power of this gravity is that the gravity that the moon exerts on earth is the dominant cause of your ocean tides. You see, when you look at ocean tides, you look at gravity in action. Another way of gravity is this. um our kids, the babies, when they learn to walk, when they crawling, they fighting with gravity, right? They fighting with gravity. Another another thing that we know of gravity is its usage in sports. Okay, it is also responsible for this. Whatever goes up must come down. If you throw an object upwards, it comes back downwards, or it comes back. Why is it coming back? It's because of gravity, right? It's because of gravity. Now, let's get into it. Now, there's something about gravity that you should know. So I'm going to talk about the gravitational force right now. Okay, I'm going to talk about the gravitational force. Something you should know about the gravitational force is that it depends on masses between objects. Okay, it depends on masses between objects. All right, and not just that, it also depends on the distance between them. Okay, and the distance between them. Okay, and the distance between them. Sorry, and the distance between them. Okay, that is the gravitational force. Gravitational force depends on masses between objects and the distance between them. So with the statement that I just said now, we are basically opening Newton's law of universal gravitation. Now let's look at it. Let's look at it. So we said it's Newton's law of universal gravitation. Of universal gravitation. Okay. Now, the law states it states that every particle in the universe attracts or is attracted to every other particle with a gravitational force that is directly proportional to the square of the distance. That is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. So remember, in the previous slide, I said gravitational force depends on on masses between objects and the distance between objects. Now, Newton's law says, the Newton's law of universal gravitation says, let's write it down now. It says every particle in the universe, maybe let me mention that in the universe is attracted, okay, is attracted to every other particle, right? To every other particle with a gravitational force, right? With a gravitational force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their masses. Between their masses. Right? Now, let's look at it. I will highlight some few things on it. So they say every particle in the universe is attracted to every other particle with a gravitational force. I'm going to highlight gravitational force, right? And remember, here we're talking attraction. Remember what we had said? We had said that gravity is an attractive force. Right? Gravity is an attractive force. So every particle in the universe is attracted to every other particle with a gravitational force that is directly proportional. It's important to note this: directly proportional to the product of their masses, and this part here, inversely proportional to the square of the distance between their masses. Okay? So this something that I think you should know by now when you do physical sciences. The laws, the definitions are somehow giving you formulas, right? Now, let's look at this one. They said gravitational force that is directly proportional to the product of their masses. Considering two objects, product. So M1 times M2, that's a product, right? Now, and inversely proportional. When they say inversely, it'll be 1 over. Inversely proportional to the square of the distance. I'm going to call the distance r, but they say the square, so it's going to be r squared. As you can see here, force is directly proportional to the product of their masses, and this force again is inversely proportional to the square of the distance between the masses, right? So now, what this means, direct proportionality means when you increase one of the masses, the force must increase. When you decrease one of the masses, the force must decrease. So it has increase, increase, decrease, decrease. Now, you look at the inverse relationship. If one increases, one decreases. And pay special attention to this part here. It is a square. So if the distance was halved, right, if the distance was halved, it'll be, remember, put it in a bracket, maybe let me write it here. The distance was halved. Remember, it is the distance squared. What is our answer here? It'll be 1 over 4, right? It'll be 1 over 4 because the distance is squared, okay? Because the distance is squared. So remember, inverse relationship, when one increases, one decreases. When one decreases, one increases. Okay? So, according to this law, if you want a greater attraction, say distance is constant, increase the mass, because when you increase the mass, the force increases. If masses are constant, to get a greater attraction, decrease the distance between the objects, meaning bring the objects closer together. Okay, now let me show you something. So let's look at this. Which ones have a greater force? Have a greater attraction? Maybe let me say which ones have a greater attraction. I'm going to maybe give you two shapes. Let me choose a gray one. Okay, and then so this is scenario 1, and then I'm gonna take scenario 2. Okay, so I'm gonna take scenario 2. Now looking at these two scenarios, which one have a greater, let's say their masses are equal. Okay, let's say their masses are equal. So this is scenario A, scenario B. Alright, scenario A and scenario B. As you can see, the distance between the two objects in scenario A is smaller than the distance in scenario B. So what is happening here? Here you are increasing the distance, right? So when you increase the distance, remember, distance is indirectly proportional to the square of force, rather, is indirectly proportional to the square of the distance. So if you increase the distance, what happens? Force will decrease. Now if you decrease the distance, what happens to the force? It'll increase. So which ones have a greater attraction? It's these ones here. Okay, it's these ones here. Okay, now let's come back to the formula. The law said every particle in the universe is attracted to every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their masses. So this gives rise to a formula. We have said before that F is directly proportional to m1, m2. Again, this F is inversely proportional to r squared. The formula therefore will be F equals G m1 m2 all over r squared. This is the formula that Sir Isaac Newton came with to help us understand the attraction between two particles in the universe. Okay, so this here, we call it the gravitational constant. Okay, this one here, we call it the universal gravitational constant. Okay, we call it the universal gravitational constant. It has a value 6,67 times 10 to the negative 1 Newton meter squared per kilogram squared per kilogram squared. Okay, so this is what Sir Isaac Newton came with, and this is the formula that you're going to use to understand the attraction between two objects or two particles. And again, to help you understand this R, we said it's the distance between the masses. For larger objects like planets, you have to consider the centers of those objects. Okay, you have to consider the center of those objects. Okay guys, so in the next videos we will be looking at calculations that will be helping you in understanding this. The examples will help you understand this. Okay, now let's look at I think I should say it should be a force between, yeah, let's look at it. Let's say it's, okay, let me use a black color. Let's say it's force between F and an object with mass m. I think I should call it mass mo. Okay, let me call it mass mo. All right, so I want us to look at this. What we know is that if I want to find the force that this mass experiences on Earth, we can call it F net. Otherwise, you can still call it F. Right? It is equal to ma. Right? But the a that we're using on Earth is 9,8. We are also going to show you how we get to that 9,8 in the next videos. All right? Now, I want to call this object. Remember, we said it has mass mo. So let me call it mass mo, and let me call its acceleration o as well. Okay, so the attraction between Earth and this object, so these are two objects, right? These are two objects or two particles, can be quantified using the formula m1 m2 all over r2. Right? So object mo experiences the force F on planet Earth, which we know. Right? We can find, this is what we call the weight. All right, this is what we call the weight. So if we say F is equal to MO and AO, in place of F we will write MO and AO. All right, and G remains. M will be the mass of F, and then M2, let's call it MO now, because we're talking force between the F and an object with, oh boy, force between F and an object with mass mo. So we're calling m1 mass of F, m2 we're calling it mass of the object with the mass mo. Now, and then we look at the distance between them, which is if this object is on planet Earth, the distance between it will be the radius of planet Earth, or yeah, the radius of planet Earth. So let's call it RE. Now, this is what we have so far. When you look at the left hand side and the right hand side, you can see we have MO, or M subscript O, or M sub O on both sides. So since we have M sub O on both sides, we can basically divide by M sub O throughout, both on the left hand side and the right hand side. Then this will result in AO equals G mass of planet Earth over radius of planet Earth squared. Right? So this is what we term the acceleration that is experienced in planet Earth. Right? This is the acceleration that is experienced in planet Earth. Now, something that I want you to know, basically we call it gravitational acceleration. Okay? So this is gravitational acceleration. So one thing I want you to know is that gravitational acceleration does not depend on the mass of an object. Right? Does not depend on the mass of an object. Right? Again, as you can see, it also does not depend on the on any other thing like distance. Distance does not play a role on what is this? Does not play a role on gravitational acceleration. Oh, sorry, let me add gravitational acceleration. Okay, and again, something that you must know is this: every object will experience the same acceleration, right? Every object will experience the same acceleration. Will experience the same gravitational acceleration. Maybe let me put it in that way. Will experience the same gravitational acceleration in any planet. So in our planet, all objects will experience 9,98. 9,8, sorry. Okay, so every object will experience the same gravitational acceleration. Okay, so this is what Sir Isaac Newton came with. This helped us to understand. Acceleration. Now, in the next videos, you will understand the relationship between acceleration between two planets, maybe planet Earth and planet Jupiter, planet whatever. All right, we will be looking at that. So this is all that you need. Oh, before I part, remember this is acceleration, so it has the units meters per second squared. Okay, it has the units meters per second squared. Okay, guys. Okay, so I hope you guys will now understand Newton's law. We haven't yet done calculations. They will be coming, and trust me, it'll be an exciting topic. Okay, it'll be an exciting topic. All right, guys. So see you next time, and bye bye.